Hello everyone. Before anything, I want to thank everyone for attending this session and listening to my presentation. This is Muhammad Saleh Jafari, PhD in Electrical Engineering from Florida International University. I graduated in 2021 and my research interests include power system modeling, dynamic studies, renewable energy, optimization, and cybersecurity. So the title of our work that I'm going to present today is Optimal Improvement of Post-Disturbance Dynamic Response in Power Grids. The table of the contents of my today's presentation would be, I would first talk about the introduction a little bit, then I go for background, then I present the proposed approach, and then I show the results of validation of the proposed approach, and I go for case study results, and at the end, I conclude this presentation. As the introduction for this presentation, we know that any disturbance in power grids would lead to electromechanical oscillations. That these oscillations would cause some fluctuations in the frequency and rotor angle of generators. Also, we know that there are like some set of control actions like governors, reference set points that determine how these dynamics would evolve after the disturbance in the power system. So if we can carefully and dynamically set these governors reference set points, we would be able to definitely enhance the overall dynamic response of power grids. So this is like the main motivation behind this work. As the background of this work, I've put some equations related to power system dynamics. So the generator is the main component that we need to model in power system. As you can see, I put the equations 1 and 2 that are like the swing equation that represents the classical model of synchronous generators. Equation 1 represents the change in the rotor angle of the generators, and equation 2 represents the change in the frequency based on the change in the mechanical input of the power system of the generators. In equation 4, I included the DC power flow that models the relation between all the generations loads using the transmission lines that we have between the buses. The governor that we use in our study is the governor model TGOV1. And as you can see in figure 1, this governor takes the change in the frequency of each generator and then compares with the reference set points for the governors that we have. And based on that, it changes the mechanical power. The equation 3 shows this relation between the mechanical power and the change in the frequency, and equation 5 shows the amount of the reference set points that is going to be set by the DC power flow. All the equations that I've been talking about so far, I mean equations 1 to 5, all of them are continuous and linear equations. So if you want to implement these equations in the optimization framework, the proposed model wouldn't be scalable because of the nonlinearity of the equations. So our solution was using the backward Euler method. So using this method, we were able to convert all these continuous equations to discretized and linear equations. Equation 6, as you can see here, is the discretized format of the governor model that we just talked about it. And equation 7 and equation 8, they are actually the discretized format of the swing equations representing the classical model of the synchronous generator. And equation 9 is the discretized format of DC power flow that we have, and equation 10 is the governor's reference set points that we are going to calculate based on the DC power flow. In this paper, we aim at minimizing the frequency oscillations in power grids by finding the optimal set points for governors. So to do so, we propose a linear programming model of power system in an optimization framework. As you can see, equation 12, which is named OPFD, tries to minimize the frequency fluctuations in any discretized time step. Subject to a couple of constraints, I just talked about equations 6 to 10 that are discretized format of all the continuous and nonlinear equations of power system. So this this model 12 OPFD tries to minimize the fluctuation in the power, in the frequency, subjects to constraint 6 to 10, as well as constraint 13 that tries to keep the mechanical power of the generators to be within the acceptable range. And equation 14 and 15, they try to tide up the frequency, the change in the frequency of power system after any disturbance, to be as close as possible to omega 0, or to the nominal frequency of the power system. In order to validate the proposed model, OPFD, and also trying to run some case studies, we need to have a test system. So we consider IEEE 39 bus system as the test system. This system has 10 synchronous generators, and each of them is of 1000 megavolt ampere. 6 of these generators are equipped with governors, and 4 of them they don't have any governors. And as you can see in figure 2, the generators that are equipped with governor, they are in gray color, and the ones with no governor, they are in white colors. And table 1 also shows all the information about the generators inertia and the governors parameters. Before going for finding the optimal set points for the governor's reference based on the OPFD that we propose in this paper, first we need to make sure that this model has the basic, it's able to capture the dynamic of power system properly. So to validate this model, we apply a load disturbance to the test system, the IEEE 39 bus system, and we compare the resulting dynamics with the simulation results from ePhasor sim in OPLRT. But the load disturbance that we consider is adding of 1000 megawatt to the total amount of the load, or 50 megawatt extra at each load. So this 1000 megawatt would be like 16% of the total load. And we apply this disturbance for 3 seconds to the power system. So here we are going to show the comparison between the results from our proposed OPFD model and the results from ePhasor sim. And so figure 3 is showing the frequency dynamics. As you can see, the solid black line is the result from our OPFD model, and the dashed gray line is the result from ePhasor sim. And in figure 4, we are showing the rotor angles. But as you can see, they are so close to each other, the results. The only thing is that the little discrepancy that you see in the results is due to the difference in power flow methods applied in ePhasor sim and OPFD. So as I mentioned, we are trying to keep the proposed model scalable. So that's why we are using DC power flow. But ePhasor sim is trying to be as accurate as possible. So they are using AC power flow. And this little change between the results is due to the difference in these power flow methods. So after validating the performance of the proposed model, we want to implement different case studies. The proposed OPFD is implemented in JUMP, which is the optimization package in programming language Julia. And as I mentioned, so far OPFD is going to give the optimal governor set points, so to dampen the oscillations as fast as possible. So we consider 2 different scenarios while we are considering the same load disturbance that we have been talking about so far. The only thing is that we are going to keep this load disturbance for 15 seconds. And also we consider this load disturbance for 2 different scenarios. In one scenario, we consider the non-optimal governor set points, and in the other one we show the optimal governance set points obtained from the proposed OPFD model. Figure 5a shows the non-optimal reference set points for the governors, and figure 5b shows the optimal one from OPFD results. But in non-optimal case, the reason that you see there is only one time change in the reference set point, which is happening at t equals 1, is that the load disturbance occurs at t equals 1 and stays constant to the end of the simulation. So because there is no other change in the load disturbance, so that's why the non-optimal reference set points would be changing only once at t equals 1 and would stay constant to the end of the simulation. But in figure 5b, which is the optimal governor set points based off OPFD results, you can see that even though the load disturbance is constant after t equals 1 to the end of the simulation, but these reference set points, they are dynamically changing based on the model that we proposed. The reason is that these reference set points, they are dynamically changing so that the oscillation of the frequency dampen as fast as possible. So in this figure, you can see the difference in the performance of the two non-optimal and optimal governor set points. So here we are showing the difference in the oscillations of the generator's frequency and rotor angles based on the non-optimal governor reference set points and the OPFD results. In figure 6a, you are seeing the frequency dynamics, and again the solid line is the result from OPFD and the dashed gray line is the result from non-optimal case. And as you can see, in most of the cases you see that the OPFD results, they are going to the steady state value faster than the oscillations resulting from the non-optimal governor reference set point. The same story is happening in figure 7, which is the rotor angles of the generators, and you can see that again the oscillations are damping faster for the OPFD results. In this slide, we show the comparison between the settling time of the oscillations in the frequency and the rotor angle of the generators, and compare the results for the non-optimal and optimal governor set points. The last column in each of the tables shows the improvement, meaning that if the settling time has been reduced, the value would be negative, and if the settling time has been increased, the value would be positive. And as you can see in the last column of both tables, all the values are negative. That shows that the proposed OPFD resulted in faster oscillations, except one case, which is generator 39. And the reason is that in this OPFD, we try to consider the overall performance, not each of the generators specifically. We didn't try to reduce the settling time each of the generators separately. We try to have the best results for all the settling time of the generators. So here you can see easily that all the values are negative, and you would see the improvement of the settling time of all oscillations after implementing the governor reference set points that we calculate based on the OPFD, proposed OPFD. As the conclusion of this presentation, in this paper we propose a OPFD method to minimize the frequency oscillations in power grids by finding optimal set points for governors. Also, we propose a linear programming model of power systems in an optimization framework, and we showed that the OPFD method results in oscillations with shorter settling times in most cases in comparison to the non-optimal reference set points. Thank you again for listening to my presentation, and I hope you find this paper interesting to read.